Hi, everyone, and welcome back to this video series on the paper by Jean-Charles Rochet, a necessary and sufficient condition for rationalizability in the quasi-linear context. And this is a part 2 where we are going to take a look at this special case, special one-dimensional case. So quick recap of what we have so far. We are discussing the situation where we have an agent and the agent submits a bid. It has a private value T and it submits a bid. Then there is the mechanism which produces some outcome X of B, and our agent gets the utility given that its private value is T and the bid was B. There is this value function. And the value function takes the T, the true private value of the agent, the outcome of the mechanism, and also the mechanism assigns a payment of B. And the statement of the main theorem, is that the rule X of B is rationalizable. And this means that submitting B equals T is the best thing, is the best action. So that U of T in T greater or equals than U of T in B for any T in B. And more explicitly, this means V of T and X of T minus P of T is greater equals than V of T and X of B minus P of B. And this is for any T and B. Yeah. So this is equivalent, like if and only if this rule X of T holds a special property with respect to this function V. And this property is called, well, it's called a C-cyclic monotonicity. Or the C is mentioning some function, but in our case, that would be a V cyclic monotonicity. So this cyclic monotonicity with respect to the function V, and the condition is that for any sequence T1 up to Tn, and assuming that Tn plus 1 is equals to T1, so this is a cycle, the sum of going from K1 to N of the following V of Tk plus 1 and X of Tk minus V of Tk and X of Tk less equals 0. So in both directions, this means that if this condition holds, let's call it condition 3, because this is the number of equation in the original paper. So let's keep that. So if the equation 3 holds, we get this. So there exists a function for payments P that would lead to this inequality being true for all T's and B's. And the converse is also true. So if there is if this P function exists, then conversely, and this condition holds, and conversely, the cyclic monotonicity also holds. Okay. So now, what is different in one-dimensional context? Or what is more special? Like, what is exactly more special about the one-dimensional? Well, as we will see, there is given just one additional condition, we can get an even we can get a very, very like full characterization of all mechanisms that could be rationalizable. So this additional condition, so okay, one dimensional, what it does mean that it means that t actually belongs to an interval from the lowest t to the largest t, and then also x is also one dimensional, so it's just in R. Okay, so there is this additional condition that would let us derive a full characterization. This condition is called Spence-Mirrorless condition. And this is a condition on the value function v of t and x. And it says that the v of t and x, this function belongs to the class of functions C2, meaning its second derivatives are continuous. And also additional condition that the cross derivative, the second cross derivative is positive. So the second derivative of v with respect to t and x is greater than 0 for all t and x. And now the statement of this refinement for one-dimensional case is the following. Given, so let me give it a name. Let's call it theorem 2. Well, in the paper it's called proposition, but I don't remember the number. So the theorem is the following. Assuming this condition, the rule x of t is rationalizable if and only if x of t is monotone. So this is a single dimensional context. So the monotone functions in one dimension is pretty straightforward thing, something this. Actually more typical, it's like a piecewise constant function. So piecewise constant monotone function would look something like this. And we will see some of these examples down below. So what we need to prove? Well, we need to prove that if, okay, so again, assuming this Spencer-Mirrorless condition, well, from monotonicity of x of t, we get the cyclic monotonicity, or more specifically v cyclic. And conversely, from again assuming the condition, and given that the cyclic monotonicity holds, we get x of t monotone. So now we can talk about the proof of this. And the proof goes into steps. So the step one is prove this for all cycles of order 2. So we will actually prove that if the cyclic monotonicity holds for the cycles of order 2, then we can get the monotonicity of x of t, and conversely, from the monotonicity of x of t, we would get the cycle monotonicity for the cycles of the order of 2. And then separately, we're going to prove that in one-dimensional context, this 2-cycle monotonicity implies the general cycle monotonicity. General monotonicity. Okay, so let's start with the first one, and it's not a hard proof. So the idea of this proof is that we are going to take a look at the integral of going from some arbitrary t1 to t2, and this the integral from x of t1 to x of t2 of the second derivative dt dx. Well, now it's going to be some renamed variables of integrations, dz, ds, dz. Well, given the Spencer-Mills condition, we know that this thing is, well, it's going to be greater or equals to 0, because the integrand is positive. And actually, well, yeah, okay. So now we can also use that V is C2. So its second derivative is continuous. And from this, we can get that it reaches its lower and upper bounds in this area. By the way, the area here is, we can just visualize it. We are integrating over a rectangle. So this is a T1, this is a T2, this is the X of T1, and this is the X of T2. So we are actually considering the integration over this interval, over this rectangle. And yeah, and then the function reaches its, because it's continuous function, it reaches its upper and lower bounds inside of this area. So we can bound this integral using this lower and upper bounds. So we can actually, okay, let's give it give this integral a name. Let's call it d. So we know that, okay, let's call L the lower bound of this second derivative. And well, then we can bound the integral by just multiplying the lower bound with the area of this rectangle. So this is going to be x of t1, t2 minus t1. So we know that this is less equals than d. And then on the other hand, we have the condition for the upper bound, which let's call it h, and again multiplied by the area of the rectangle. Look at this. Okay, so how are we going to use this bound? We are just going to actually compute this integral now. And computing this integral is pretty straightforward, because again, this is integrating a continuous function, so we can apply the basically Newton-Leibniz integration formula. So let's do it step by step. So let's compute this d. Okay. So the d now is going to be this double integral of the second derivative, ds dz. So let's integrate first using the inner. Let's do the inner integration. So we are going to keep the outer integration, and we are going to get one of derivatives out, and then we have this the difference. So this is going to be dv by dt of some s. We're still integrating with respect to the first variable, but the second variable is now replaced by x of t2 minus dv dt of x s and x of t1. And this is the integral over s now. So now doing the same with the remaining integral for the first one and for the second, we get the following. We get the v of t2 of x of t2 minus v of t1 x of t2. Now we have a minus sign here, and we get the second one, v of t2 x of t1 minus v of t1 x of t1. Okay, so let's take a closer look at this. Well, what we have here is we wanted to make it we want to use the cycle of monotonicity here. So let's rearrange the terms in the way that would reveal that this is actually the same thing as this the cycle monotonicity for the cycle of 2 of the order 2. So how can we do that? Well, we have, well, basically it's just minus. Let's extract the minus. And then we have the usual stuff. We have v of t2 x of t1 minus v of t1 x of t1, right? Plus v of, now we extracted the minus, so this minus is extracted. So now we have v of t1, which is actually n plus first. So for the cycle of 2, order 2, the n plus first element is t1 x of t2 minus v of what's the one remaining, t2 x of t2. So we know that if the cycle monotonicity for the cycles of order 2 holds, this thing would be less equals 0. And given that there is a minus in front of it here, we can also say that this would be this would be greater than 0. So now let's go back to this condition, and we know that well, we certainly know that this is greater than 0. Just because we were integrating a positive function here. So let's consider the first inequality here. So what we can get from this first inequality is saying that, well, if x is monotone, right here, if x is monotone, well, this is going to be larger than 0 if x is monotone. So we have it here. And given that this is going to be positive number when x is monotone. We would also bound the d to be greater than 0. And this is what we wanted to prove, that we get the cyclic monotonicity condition. So from the first inequality, we get the proof for that if the function x of t is monotone, then we get the cyclic monotonicity for the cycles of order 2. And we can get the converse of that from the second inequality here. So from the second inequality here, we are saying that given that the cyclic monotonicity for cycles of order 2 holds, then d is going to be greater than 0. And then given that d is greater than 0, then we also get that this thing is greater than 0. And this thing to be greater than 0, it must be that x of t is monotone. So this way we actually prove that we have both in both directions, that monotonicity of x implies cyclic monotonicity of order 2 and the other way. So now we want to take a look at the part 2 of this proof, and we need to prove that in one-dimensional context, the two-cycle monotonicity implies general cyclic monotonicity. This proof is a little bit more tricky, but also not too hard. So we are going to prove this by recursion. So we already proved that our theorem holds for the case of n equals 2 for the cycles of order 2, so nothing to prove here. So what we want to do now is we want to assume that it holds for some larger n, just for some n, and prove using this and the condition for the cyclic monotonicity of order 2, we would prove that for the proof for n plus 1, for the case of n plus 1. So how can we go about this? Well, let's write it out for the case of n equals 2. So for the case of n equals 2, our cyclic monotonicity condition, we are going to assume it, because this is the step in the induction. So we are going to assume that from the sum from k going from 1 to n, we have this k plus 1 x of t of k minus v of tk x of tk is less than 0. Okay, so now let's consider the case of n plus 1. So the difference, so when we will write this, the sum for the same sum for the k goes from 1 to n, the only thing that is going to change is what happens with the cycle itself. So here, in this case, the cycle ends up in a way that n plus 1, tn plus 1 is equals to t1. But here in the second one, in the second line, there is not going to be like this. We are running the sum until, I'm sorry, I have forgotten to write. The sum here runs until n plus 1, and the cycle is going to happen like on the next one, on this tn plus 2. So let's write it out again. So this is going to be pretty much the same formula. And I just wanted to expand it, keeping the sum of all elements up to n. And this is going to be the usual one, tk plus 1, x of tk minus v of tk x of tk Okay. And well, there is this last n+1 case. So for this n+1 case, we have v of, well, we need to cycle from n+1 to t1. So this is going to get n of t1, x of t1, and t of n+1 minus v of tn+1 and x of tn+1. Okay. So, well, what I want to do is I want to use the previous one where we have this cyclic monotonicity condition for the order n. So how can I do it? The only difficulty here is that this element here and this element here are different. So this one here is v of tn x of t, no, actually this one is tn+1 x of tk. And this one here was v t1 of x of t. Well, this one is going to be n. Right, and this one also going to be n. So, well, in order to complete this sum, I want to take this thing and just add and subtract it here. So I'm going to, yeah, I'm going to bring this thing down here. So I'm going to add it and subtract t1 and x of tn. And I'm going to subtract the same thing, t1 and x of tn. So let's take a look what we have. Now we have this thing. Let me use another color. This one. If we take the green one out and put this thing back, this is going to give us the cyclic monotonicity of the order n. So this thing is going to be less equals than 0. But we also would need to have, so there's going to be d for n, which is going to be less equals 0. And we are going to be left with the following. We would have, let's see, we would have v of t1 x of tn+1. We also have minus v of tn+1 x of tn+1. Well, we also have this green one, which is v of tn+1 x of tn. And we also have the last one, v of t1 and x of tn. Okay. So quite similar to the proof for the cycle, for the monotonicity for the cycles of order 2, we can now consider this integral. The integral runs from t1 to tn+1 and also goes from x of, let's see, tn to x of tn+1 of this second derivative, dv dt dx of s and t, oh no, s and some z, ds dz. Well, again, by the, let's just do the computation here. So we are again going to expand, to use the Newton-Leibniz formula for integrating this thing. So we will end up with, let's see, v of tn+1 and x of tn+1 minus v of t1 and x of tn+1 Now we will have the minus sign and some more brackets. So this is going to be v of tn plus 1 and x of tn minus v of t1 and x of tn. And again, we know that because we are integrating a positive function by this mirrorless Spence condition, we know that this thing is greater than equals than 0. So now our task is to compare this and this and see like what's the relation between them. Okay, so let's just find the thing one by one. So we have this here. We have this one here, right? We have this one here, and we have this one here. So 4 stars, 4 stars. So the only difference is that we should just flip a sign. So this this whole thing, let's call it small d, is like, let's call it minus d. So in this case, this is going to be d, and this thing is also going to be negative. And then we get what we wanted. We got that this full sum, this cycle monotonicity for kn going to n plus 1 actually holds, because both components, this one and this one, are negative, so the whole sum is also negative. So we get our the sum from k1 to n plus 1 is equals to 0. I'm sorry, less than equals 0, and this completes the proof. This completes the proof. So we have that in two-dimensional context. Oh, wait, yes. So again, there was a subtle point here that also x is monotone. So when x is monotone, we get our signs in the correct way, and then we get other signs in the correct way too. So we have our proof. And now I want to just show some examples and connect this to a more commonly known condition for rationalizability of the x of t, especially in the auction theory. So let me show you. So what we have now is that we know, first of all, we know that x of t needs to be monotone. On the other hand, we have also that this v capital of t, the thing that we introduced in our previous video, this thing is the one that is this is the indirect utility. So this is u of t and t. So when we have this rationalizable mechanism and sending our private value as the bid, we get this u of t and t, and this is the connection that was mentioned in the end of the previous video. And we know that this is maximizing over b of v of t and x of b minus p of b, right? Well, we also mentioned in the beginning of the previous video the taxation principle. And the taxation principle says that, well, in fact, this mechanism, the truthful mechanism, would be presented to the agent as the as the menu of choices, where the choices looks like some x1 and corresponding p1 and so on. And therefore, we can also write this in a very interesting way. We can say that this v of t is the max over this menu. So over j belonging to this menu of this v of t and xj minus pj, right? So there are two cases that we need to take a look here. So the first case, first interesting case is when x of t is a good function. Let's say C1, so it has continuous derivatives. Well, in this case, the taxation principle is basically saying that we have x of t. So it could be, well, it's a continuous function. And then for a given value of x, we get the p of x, actually not the p of t, but the p of x. So remember, by taxation principle, we cannot charge different prices or different payments for the same amount of stuff, right? So we can also rewrite this v of t as the max over x with v of t and, well, x minus p of x, right? Well, let's do like a little bit of sketchy math here and just compute this first order condition on ds. And remember that v is kind of like a good function with respect to x, so we can assume that. So now we can get something like this, that dv, well, let's compute the derivative of, well, yes. So the first order condition, optimality condition for over x would look something like dv of t and x dx minus dp over dx equals to 0. So this is the optimality condition over x. So now the thing that I want to try to address is that dv, I want to compute the derivative of v t dv dt. Okay. Well, this is going to be d by dt of vt and x of t minus p of x of t. Okay, so, well, this x, remember that by the taxation principle, we are viewing this as if the agent picked the optimal x for this given t. Okay, and therefore this derivative looks like this. It's going to be the derivative with, like, the explicit derivative with respect of t and x of t. But then we also want to take care of this the dependency of t with of x on t. So this is going to be dx by dt, and the same thing here, dv. Sorry, this is going to be dp by dx times dx over dt. And this, so I will remove this to make it a little bit less cluttered here. Well, we have dv by dt plus, well, we have dv by dx minus dp by dx times dx dt. And now remember that because of this maximization, we have this condition. So this thing cancels out, and we are left with just explicit derivative of v with respect to t. So we can write it a slightly different way. We can say that the derivative of capital V with respect to t, which is the only variable there, equals this derivative, like explicit derivative of v small v with respect to t, and the x of t is just there. And this is known as the envelope theorem. So the envelope theorem is saying that if there is a maximization involved in deciding on the value of x, then well, the derivative of the value function is equal to the derivative of t of this v and t of t and x, where we optimized over x already. So this derivatives, the full derivative of value function is equal to this explicit derivative of this value function. So this is indirect value function. This is the value function. Well, in fact, this theorem holds in a more general case when x is just a choice set. So there is this a little bit later paper by Milgram and Siegel, which is, as far as I remember, called envelope theorem for arbitrary choice sets. And what they say in this paper, it's the paper from around 2003. So in that paper, they cover a lot, but the main theorem in that paper is saying that for this to hold, this statement of envelope theorem, for this to hold, the x of t could be an arbitrary choice set, including a discrete choice set. And it's actually pretty easy to see intuitively. For one-dimensional case, we can draw it like this. So we know that v of t is, the capital V of t is a maximum over j in the menu of v of t and x j minus p j. Well, if j is just a choice set, like maybe a discrete choice set, then this is going to be a family of functions indexed by j. So this would look something like maybe like this. This is going to be for j equals 1. And this is going, let's say, for j equals 2. And maybe this is going to be for, I don't know how to draw it well, but yeah, let's do something like this. This is going to be for j equal 3, and this is going to be for j equal 2. Well, the capital V of t is going to be the envelope of this functions, and the upper envelope specifically. So we are taking the maximum. And here we can see that, in fact, there are those parts where the envelope coincides with one of the functions from the family, and well, and around here, it's pretty obvious that the derivative of the envelope is equal to the derivative of that one curve which envelope happens to coincide with. So there are just the special points where there is a jump in those in the derivatives, but in the derivative of v of t. So this is going to be v of t, and we can draw this the derivative of v of t, v prime of t. And this v prime of t is going to, okay, so this is not perfect drawing, but bear with me. It's going to go something like this, maybe like this. There's a jump, there's another jump, it goes like this. And because there are those jumps, if every component, every function v is a nice function with respect to t, such as the function is continuous and maybe even differentiable, then we can also represent the v as the integral of its derivative, because those jumps, they are finite jumps and they don't really contribute to the integral. So this is the integral statement of the envelope theorem. Envelope theorem, saying that basically this Newton-Leibniz formula holds for the envelope itself. So we can write something like v of t minus, well, it's a constant plus the integral. Well, let's do it a little bit differently. Let's assume that there is some starting point v of t0 equals the integral from t0 to t, and of the derivative of v t dt, or let's use a different variable of integration, s ds. Well, but we also found that this derivative of capital V is the explicit derivative of the value function with respect to t. So this is giving us t0 to t, v prime with respect to t explicitly of x, and x of t s ds. Well, and from this we can finally get this this very famous formulation of this one-dimensional payments, because remember we said in the previous video we found that the way we can get this function of payments is by setting it to be v of t x of t minus capital V of t. So substituting it back here, we will get that it's going to be v of t and x of t minus p of t, and this is going to be plus just v of t0, which is basically just a constant, and this thing is going to be equal to this integral from t0 to t of v prime t of s x of s ds. And we get this final p of t equals to some const plus plus the v of t and x of t minus t0 to t and this integral. And this is a formulation that I believe is also known as the Meyerson's lemma. And let's just visualize it with some plots with some very specific examples. So first, let's consider the simple case, the linear case. Well, in the linear case, we have v of t and x equals just to t times x, right? So remember that x is supposed to be monotone. So now we have, yeah, well, we need to check the Spence mirrorless condition here. Well, yes, the second derivative here is equals to 1, so it's positive. So dv, the second derivative of v with respect to t and x is equal to 1. So this is certainly larger than 0. So now we have this plot of x of t and t. And the interesting case is when this this function is actually piecewise constant, because like for example, in the context of the auctions, in a single item auction, that would be the winner of the auction getting x equals to 1, and if he outbids everybody else. But in the other case, it's going to be 0. So more or less interesting case is when this is a step function. So let's assume this step function. Okay. So from here, we get that so let's take a look at the v of v prime t. So actually this happens to be exactly that. This happens to be v prime t. So now in this case, we know that this v capital of t is going to be this integral of v prime t and x of s ds. So where's this integral? Well, this integral is this area. So let's assume this is the t. So this area is going to be the v of t. Okay. And remember, this is this indirect utility. Indirect utility. Well, also we have another thing, is that the payment p of t is equals v of t x of t minus v of t. And in this linear case, this is going to be t times x of t. So remember, this is sorry, this is not the best drawing. Just get this out. So this is going to look like this. So this is the x of t. And well, this t times x of t is just this full rectangle here. So I will use let's use some other color. Let's use this one. So this the area of this full rectangle is going to be this thing. So this is the area. Well, and then we see that the payment here is the full area minus this green area. So the payment is here. Well, and this is a super well-known result in auction theory, and this is in particular relevant to the difference between the GSP auction, GSP versus the VCG auction. So the VCG auction is the truthful auction. So the truthful auction, as we know now from this characterization, the truthful auction is the one that should be charging this red area. But in the GSP auction, we are actually charging the winner here. We are charging it according to like the second price. So this is going to be charging this red area plus this additional part, this additional part of green area. So this is why basically the GSP is not truthful. So they both have the same function x of t. X of t is the same, but the payment is not right. Okay. So I wanted to just show another couple of examples of maybe less practical use, but also interesting to take a look at. So what is let's do example 2. So that one was example 1, linear case. Example 1. So in example 2, let's take a look at what is going to happen if we take v of t and x equals, let's say, to t squared times x. So remember, this is still one-dimensional context. So what do we get? The second derivative of v with respect to t and respect to x is going to be, well, it's going to be 2t, right? Okay, so let's for convenience, let's just also add 1/2 here, so we would get just t. Okay. Well, this is still positive if we exclude the 0. So let's assume that t goes from maybe 1 to, I don't know, to 100 or something like this. So not a problem. So this Spence-Miller's condition still holds everywhere except for the 0. So now we can follow the same pattern. So now we have that let's assume that x is a monotone and x of t is a monotone, and it's like a piecewise constant function. So it's going to look something like this. And just for convenience, let's say this is going to be the x1 equals to 1 and the x2 equals to 2. Well, now we need to again to build the same visualization for this, but this time the derivative of v with respect to t and x is going to be x times t. right? Or better say t times x. T times x. All right, so now we have well, we have for x 0 equals 0, this is going to be flat like this. Then here we are going to get something like this. It goes here, assuming this is like the tangent of this is 1, so this is going like this. And then there is a the tangent of 2 starting from here. So it's going to look something like this. It goes from here like this. Okay. Well, now let's again find our integral. So in this case, v of t is going to be the integral from 0 to our t, and let's assume that t is actually here. T of v of t, the derivative of v with respect to t of some s and x of s ds. So, well, now we have this green part looking like this. This is this thing, this is this thing. So now this is the green part. Well, and remember that the payment is v of t and x of t minus this v capital of t. But we can also represent this this v of t and x of t as the integral from 0 to t, but this time the only small difference is that it's integrating with over s, but the x of t, not x of s, ds. So this integral is the area under this curve, right? So so this one in the previous picture, we had this magenta color for this integral. So the magenta color is the area of this thing, right? And then the payment is the difference between the magenta and the green. So this time, this is the payment. Well, let's do one more. Example 3. So let's take v of t and x equals to log of 1 plus t times x. Well, again, d2 of v over dt dx is going to be equal to 1 over 1 plus t times, oh no, that's it. So this is again greater than 0. Well, when t greater than 0, so everything is fine here. So again, let's consider the monotone and piecewise constant allocation rule x of t. Same thing. It's going to be 1, 2, and 0. And let's draw this v prime t with respect to, okay, this is going to be t and x. And well, this is going to be x over 1 plus t. So again, this is going to look something like this. It's going to be constant 0. Just let me use the same colors. Right. So this is going to be constant 0 for x equals 0. For x equals 1, it's going to be 1 over 1 plus t. So this is something that goes, I don't know, something like this. So this is it. And then in this part is going to be 2 over 1 plus t. So this is going to be something like this. Here. And by the same arguments, we get that the magenta area, the value is going to be this stuff here. Let's assume this is t. So we get this magenta. Now we have the green area is the area under this curve. Okay. And then the payment is this, the difference between those two. Right. So this is it for the one-dimensional case, and we will discuss the multidimensional case in the next one.